say a big thank you to him. I learnt and continue to learn a huge amount from Aaron, and I was really very lucky to have such a great PhD supervisor and teacher. So this talk is my attempt to say thank you by continuing one of Aaron's unfinished thoughts. The subject of my talk is Aaron's proposal of loop-closing semantics, and how it can explain the origin of intensional states. This is very recent work, and it's unfinished. So this is what I'll talk about. First, I need to communicate why there really is a deep problem of naturalizing semantics. Then I'll discuss Aaron's proposal and extend it in various ways. Then I'll apply the theory and show how it successfully naturalizes some semantic properties and therefore can explain the origin of some intensional states. Okay, let's begin. So say I believe the temperature of the room is 20 degrees. Now obviously my belief is not the same thing as the temperature of the room. In other words, my belief refers to or represents some other thing. And my belief doesn't refer to air pressure or the time of the day. It has focus. It refers to a specific subset of the world. And my belief can be wrong. It can misrepresent the world. It has semantic value. It can be true or it can be false. And the question is, can we reductively explain these intensional properties of reference, focus, and value in terms of non-intensional properties? I'll tackle this question by deliberately avoiding the complexities of the human mind. Instead, I'll focus on simple artifacts such as thermometers and thermostats. Now, we understand these devices very well. So if we can show how simple artifacts can instantiate some intensional properties, then we'll begin to have a very clear understanding of how reductive explanations are possible. Consider an ordinary mercury thermometer. A necessary condition for a thermometer to measure temperature is the lawful variation of some part of it with temperature. For example, the design of a mercury thermometer exploits the natural law of thermal expansion. This observation forms the theoretical core of a family of information semantic theories of content. That core is definition IS. Information-bearing substate X refers to Y if Y reliably causes the state of X. Now, this is a crude causal theory with well-known problems. I'll use it here as a straw man to introduce some key theoretical problems that bedevil any attempt to naturalize intensional phenomena. Consider a complex Rube Goldberg machine. It's one big complex chain reaction. Imagine, if you will, that this chain ultimately affects a thermometer submerged in some liquid. The thermometer's mercury column reliably co-varies with all the upstream parts of the Rube Goldberg machine. So according to IS, the thermometer refers to all these reliably co-varying parts, that is, the conjunction of all the features. But we don't need complex Rube Goldberg devices to make this point. The rate of evaporation from a liquid surface also reliably co-varies with its temperature. So, according to IS, a thermometer would also refer to a rate of evaporation. So the semantic content of a thermometer is indeterminate according to IS. It fails to explain semantic focus. So stick a mercury thermometer in a bowl of dry ice. The mercury freezes solid and indicates the wrong temperature. But the volume of solid mercury also reliably co-varies with temperature. The expansion coefficient just happens to be about half that of its liquid state. So this isn't a case of misrepresentation according to IS. It just so happens that the manufacturer's calibration assumed that normal circumstances prevail. If X reliably causes Y, then Y must be a veridical or accurate representation of X. so IS, by construction, cannot explain misrepresentation. In the literature, this is called a disjunction problem, and I explain why in the paper. So here's another problem. Imagine you are a man from the moon, and you find this strange artifact on the ground. What does that scale represent? You experiment and discover that its reading is reliably caused by temperature. So now you have an aha moment. The scale must represent length, and the purpose of the device must be to measure the thermal expansion of mercury. Now we know this conclusion is wrong, but the point is this. The very same relation of reliable causation supports a transparent and opaque semantic interpretation. The transparent reading is where we take the length of the mercury column to be a window onto something else, namely temperature. The opaque reading is where we take the length of the mercury column as simply representing itself. So we have a problem of semantic duality. Given that y reliably causes x, then IS claims that x refers to y, the transparent content. But x also refers to x as reliably caused by y, the opaque content. Now, IS gives no reason to pick out the transparent rather than the opaque reading, so it cannot even explain why an information-bearing state represents something other than itself. Now we can have fun identifying opaque readings for all kinds of measuring devices, and I explore some in the paper. But the point is this. Semantic properties are not reducible to reliable causation, and any reductive theory of intentionality needs to deal with these problems of conjunction, disjunction, and semantic duality. Let's now therefore turn to Aaron's proposal. Now Aaron's starting point is Tarskian model theoretic semantics. Aaron proposes that we generalize Tarski's approach by considering not just formal languages, but all kinds of representational systems used by agents to act in their worlds. Aaron also proposes we consider the causal links between the agent and its loop-closing worlds, which are those worlds in which the agent achieves its goals. Then we can set up a Tarskian-like mapping between the agent's representations and structures in its world, where the purely formal correspondence is further constrained by causal links. Now Aaron gives us a sketch, so let's try and add some more detail to it. First, we need some way to represent the causal structure of loop-closing worlds, and my pragmatic choice here is causal graphs, borrowing from modern manipulability theories of causation. Now, of course, there's no time to delve into this theory, but very briefly, a causal graph is composed of vertices and edges. The vertices denote variable properties of invariant things, and edges between vertices denote a relationship of direct cause. And with every vertex we associate a function, which specifies how the variable at that vertex is determined by its parent in the graph. So here's a simple causal graph that specifies the causal structure of what I will call a control mechanism K. It consists of 4 information-bearing states. B denotes a belief-like input. It's like a belief because it's an input from the world. And at this stage, that's all we mean by this name. I'm not claiming this state has any intentional properties as yet. D denotes a desire-like state. And epsilon denotes an error-like or comparison state. The idea is that epsilon is a discrepancy measure between the belief-like and desire-like states. A denotes an action-like state. And the control mechanism outputs a null action if and only if its error state is 0, where 0 means that the belief-like and desire-like state are equal in some appropriate sense. The null action is inactivity, such that A is not the direct cause of anything in the world. Now in what follows, I will work up to understanding what intentional properties control mechanism K may instantiate. So I'm simplifying and avoiding talk about agents or minds, and instead focusing on the simplest possible causal structure that might support intentionality. Later this may form the basis of some kind of compositional semantics. So this is a bit abstract, so let's consider an example. A thermostat-controlled domestic heating system is a mechanical instantiation of the causal structure we just defined. Its physical states, such as the position and rotation of its spiral bimetal coil, are information-bearing states, which map to the causal structure we just outlined, and there are more details of that mapping in the paper. Now we form a loop by connecting a control mechanism to the world in the right way. It's fairly simple. We connect the action output to some part of another causal graph, which represents the causal structure of some world, and then we connect the world back to the control mechanism. Here is an extremely simple example that has two vertices. It describes a heating system connected to a room with an open window. The heater affects air temperature, but so does the open window. The function set is a mixture of differential and algebraic equations, but in general the relationships could be pretty much anything. And this isn't even a particularly good model of a domestic heating system heating a room. It's highly idealized. But the point is this: the functions implicitly define feedback dynamics, so the values of variables at the vertices change according to the loop's dynamics. And a model is any world W that can form a loop with control mechanism K. But we're interested in a special class of models, the loop closing models. So we want to pick out the subset of models in which K's desire-like state is satisfied. And we do this with the concept of inactivity. Inactivity is when K's error state is 0 and its action output is null. In other words, K is in a state of equilibrium with its environment. For example, look at these dynamic trajectories generated by the loop I showed you on the previous slide. The first graph is when the window is shut. This is an ultimately inactive trajectory. The second graph is when the window is repeatedly opened and closed by some other causal agent, letting in cool air. This heating system fails to reach its set point, so this trajectory is not ultimately inactive. But identifying ultimately inactive loops is not enough, because K may not be causally responsible for this result. The room temperature might hit the set point by accident or due to the actions of some other causal agent. So in what circumstances is K the causal agent? We can answer this question in terms of interventions on causal graphs, which are ideal experiments to decide whether X causes Y. I'll skip the details here, but in the paper I specify conditions under which a variable is the actual cause of another variable, where actual cause is the technical term that captures our intuition of sole causal responsibility. We can then define when control mechanism K is loop controlling, in the sense that its actions are the actual cause of its own input. We can now define the set of loop closing models. A loop closing trajectory is ultimately inactive in which K is loop controlling, and a world W is a loop closing model for K if it generates at least one loop closing trajectory. Now the loop closing models are special because they are those worlds in which the control mechanism manifests its causal powers without interference or in a pure manner. In this sense, loop closing models are like natural experiments to determine what K can do. And the point is this: in loop closing models, K is causally responsible for its own inactivity. Here's a summary diagram. The set A consists of causal graphs that represent loops in which K acts. We can pick out the subset B that are ultimately inactive. We can pick out another subset C in which K is loop controlling. The intersection lambda are the loop closing models, in which K is the actual cause of its own inactivity. This metaphor might help. Consider a key that you find on the floor. Its shape and size implicitly defines the possible locks it can open. In a similar way, a control mechanism implicitly defines the possible worlds it can control. Those worlds are the loop closing models for it. Now, the loop closing models contain an important item of information that we'd like to extract. So there are many questions we could ask of the set of loop closing models, but here I want to find out what features must be in the world for a loop to be loop closing. For example, this loop closing model has 6 features in its world, but some of these features are surely irrelevant to loop closure. And roughly speaking, we proceed as follows. We generate the conjunction of features for each model by tracing the appropriate causal paths. Let's call this the conjunctive feature. We then form the disjunction of every conjunctive feature. And this disjunctive feature is a property of the set of loop closing models. And in general, it will be a large and complex expression. I define the manipulable or controlled feature as the minimal disjunctive normal form of the disjunctive feature. And we can compute the manipulable feature using any kind of algorithm that minimizes Boolean functions. And the satisfaction of at least one conjunctive clause of the manipulable feature is a necessary condition for a loop to be loop closing. So the manipulable feature describes some thing or collection of things that must be present for control success. In the paper, I argue that if we consider all possible loop closing models for a heating system, then its manipulable feature converges to temperature. So a heating system manipulates temperature and not air pressure or any other covariant feature that might be present in any particular situation. Now, this might strike you as an underwhelming result until we consider that the definition of manipulable feature helps decide much less obvious cases. Plus, the argument shows that a thermostat manipulates temperature not in virtue of the intentions of its designer, or the uses to which it is normally put, or the reasons for its existence and persistence as an artifact, or the method by which it acquired its causal properties, but rather in virtue of the kind of thing that it is. Now, clearly, I'm obliquely referring to some other theories of content there. So this is all rather abstract, so let's jump to an example of Fodor's. Imagine you're in a park in the evening and you see a dog. It causes the symbol dog to get instantiated in your mind. Later, another furry four-legged creature crosses your path, just like in this picture, and you also think it's a dog. But it turns out it's a cat. You were confused by the dim light. Now, according to naive theory IS, the symbol dog refers both to dog and cat in dim light because both these features of the world reliably cause it. In fact, many other things could be part of the symbol's extension, including cardboard dog. So I'll use Fodor's example to help explain the meaning of a manipulable feature. Again, to avoid the complexities of the human mind, we'll instead consider a Fodor machine designed to scare dogs away. It has a camera as an input and a loud siren as an output. A software classifier maps the camera input to a Boolean B, and we as the designers intend B equal 1 to indicate the presence of a dog, and B equal 0 to indicate the absence of a dog. We build the classifier from data using some kind of machine learning algorithm and get a 5% false positive rate on the test set. B is then compared against an internal constant, D equals 0, and if B doesn't equal D, then it outputs A equal 1, which is an action to turn the siren on. Otherwise it outputs a null action to turn the siren off. So the Fodor machine is a negative feedback control system which has a causal structure that is captured by our definition of a control mechanism. Now let's test the machine in the park. As we hope, dogs get recognized, the siren blares and they run away. But in dim light, cats are a false positive of the classifier, so cats also get scared off, which of course wasn't our intention as designers of the machine. So given these loop closing models, the manipulable feature for the Fodor machine turns out to be dog or cat in dim light. We now place a cardboard dog before the machine. The siren blares, but of course the cardboard dog stays put. The machine cannot be the actual cause of its own inactivity in this situation. So cardboard dog is not part of the manipulable feature. Let's assume for a moment that the Fodor machine states in fact refer, in the semantic sense, to its manipulable feature. Hence, in the presence of cardboard dog, the machine's belief-like state indicates the presence of dog or cat in dim light. But, and here's the punchline, no such thing is present in its world. Hence, not all reliable causes of the belief-like state are part of its extension. The belief misrepresents the world, and control fails. We could say that, in these circumstances, the Fodor machine has a false belief. We can do what this example suggests and define Tarskian-like structural mappings between the control mechanism's internal states and its world. And the manipulable feature is the key concept that allows us to construct non-circular, reductive definitions of some semantic properties. We can define the semantic content of belief-like, desire-like, and action-like states in terms of the manipulable feature, and the manipulable feature is ultimately a property of the causal powers of the control mechanism. And for some of the technical details of this mapping, please see the paper. Now we know that naive causal theory IS failed. How does loop closing theory fare on the problems we identified at the start of this talk? Loop closing theory explains semantic focus as a consequence of the fact that information-bearing states get recruited by control mechanisms to manipulate specific subsets of the world. So for example, a heating system manipulates temperature, but not air pressure or rate of evaporation and so forth. And for example, the Fodor machine manipulates dog or cat in dim light, but not cardboard dog, and so forth. IS couldn't pick out the relevant subsets of the world. Loop closing theory, in contrast, can. Loop closing theory explains the possibility of misrepresentation as a consequence of the fact that the control mechanism can be active and therefore instantiate control states that refer to its manipulable feature without the manipulable feature actually being present in the world. Error is therefore possible because not all reliable causes of a belief-like state are part of its extension. So for example, the Fodor machine blaring its siren at a cardboard dog, this is a case where the machine has a false belief that a dog is present. Loop closing theory therefore can avoid the disjunction problem. Now the problem of semantic duality raised the issue of why any state refers to something else and not itself. Duality arises because the same relation of reliable causation can be used in different ways. For example, measuring temperature or calibrating the thermal expansion of a bimetal coil. The point is this: information content is fixed by information users. A loop closing theory takes the stance that control mechanisms use their states as means to particular ends. So for example, a thermostat's coil as part of a heating system represents temperature because the heating system in fact manipulates temperature. It does not manipulate the position of its spiral coil, and nor does its activity instantiate a calibration use case. The problem of semantics is sometimes posed as breaking out of the intentional circle of human practice and meaning. Loop closing theory shows that some simple causal structures in fact instantiate intentional circles, independent of human practice and meaning. Okay, we can now conclude. I hope I've given you some idea of how loop closing semantics successfully reduces some intentional properties to causal powers. The key idea is that a control mechanism implicitly defines a manipulable feature that is necessarily present for control success. Now, the discovery of viruses challenged and clarified our understanding of the concept of living things, and control mechanisms are another simple edge case. For example, loop closing theory justifies the claim that the Fodor machine has states that refer to the presence or absence of dogs entirely independently of us, even though we built it. But of course, the Fodor machine doesn't refer to dogs in the way we do. The machine has no concept of a dog. In fact, it has no ontology at all. Should we therefore deny that it refers to dogs? We could argue that a virus is dead rather than alive, but people would agree that this pre-theoretic division of the world into living and dead things is somewhat quaint. Here's a quote from Aaron. He says, "I claim that there are no well-defined concepts that correspond to our normal use of these words. Rather, there are many different features to be found in contexts in which we ordinarily talk about meaning, and different subsets of those features can occur in connection with control states of various kinds of machines." The only point I'd add is that control mechanisms, such as domestic heating systems, are qualitatively different from passive systems, such as thermometers. Control mechanisms have semantic properties in virtue of their causal powers. Simple measuring devices do not. So there's an important schism in the design space of possible things. Simple control systems are where symbolic representation first gets off the ground. So the origin of intentional states is in kinds of goal-directed activity. Human minds just happen to be one rather complex case.